Hello, 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 everybody, and welcome back. We're looking at problem 2 now on part 2 of our 2011-2012 Alberta Math Contest. In quadrilateral ABCD, AB is parallel to DC, so we got another trapezoid here. Trapezoid, certainly one of the best kinds of quadrilaterals. Okay, so AB, they'll probably go clockwise, so CD. Okay, prove that PA over PB. Okay. So P is a point on AB, so that I don't know why they didn't say that ahead of time, but oh well. I'm not the guy who writes their questions. So that DAB, CBA, those are angles that are not. We got DPC. So P is somewhere up here. Maybe. Okay, so P is somewhere up here. And we've got use pink. This angle is the same as the ones in the upper corners. Okay. So what can we do here? And sorry, what do we need to do? I skipped over this. I need to show that PA over PB is the same as PD over PC squared. Okay, I'm starting to think, just because they're talking about side lengths, I'm starting to think about congruency. I'm starting to think about similarity. So maybe some similar triangles are kicking around here. We do have three angles that are the same. So definitely something to think about. All right, now, a nice property of trapezoids that you can prove if you're not familiar with, it's that the angle up in one of the corners next to one of the parallel sides and the corresponding angle on the same side parallel to the other parallel side, or next to the other parallel side, these two are supplementary angles in that they both add up to 180. You can see this by extending this just a little bit. And then the Z theorem, as I'm often fond of pointing out, says these two are the same, and then these add up to 180. So if we were to give a name to our pink angle, maybe call it theta, we can definitely say that this red angle down here is 180 minus theta. Same with this one here. Okay. So does that help us at all? Not that I can really see. Here's something. Let's not use that. I thought that might be useful. Let's call this. I'll just use dots. So if this is red dot, okay, then here we have an exterior angle to the triangle ADP. Okay, which means that this exterior angle is the sum of the opposite interior angles, the ones opposite the side that you're, or the angle that you're extending past. So this needs to be the sum of theta, well, we know it's the sum of theta, plus the red dot, so we get the little red dot here. And similarly, I suppose we could use blue. We put the blue dot here, we'll get the blue dot here. And now we can use the 180 thing to say, all right, blue dot plus theta plus red dot must be equal to 180. So we can get the blue dot here and the red dot here. And that'll open up some similar triangles. Now, it is a written contest, so we should at least write this down a little bit. I'm going to actually drop the theta and just make it a pink dot. Okay. Put a pink dot there. So we can see angle DPB is the same as angle DAP plus angle ADP, okay, which is pink dot plus this initial red dot. I'm gonna show it to you one more time. Okay, but it's also equal to angle BPC plus angle CPD, and this one here is a pink dot. So angle BPC must be equal to red dot. That is to say, it's angle ADP. Okay, so that's why we get red dot there. Similarly, we can see that angle BCP must be the same as angle APD. Okay, so that's these blue dots. Okay, finally, we know since it's a trapezoid, because we were told the parallel sides, we can see that angle PBC plus angle BCD must be 180. And so this one here is that pink dot up in this corner here. But then 180 is PBC, pink dot, and now I'm going to break down BCD into BCP and then PCD. So breaking pink dot, the blue dot we made, and therefore this has to be red dot. Okay. So PCD has to be the same as the red dot, so we'll say angle ADP, and so on. And so now, having justified that, we can just work with this triangle, or with these sort of triangles here, without too much worry. Okay. You should make a note of that, so we can say APBCD, but triangle APD, so the middle one is the blue one, is similar to B. Start on the pink one, go to the blue one, end at the red one. And it's also similar to start at the pink one, go to the blue one, end at the red one. Okay, so now I've got 3 similar triangles, and similar triangles are nice because we can work with their ratios. Okay, so since these triangles are similar, what can we see? Well, we want to talk about AP, right? So AP is the so we want to talk about AP, PD, or DP, CP, and BP. So we'd like to use these. So AP, I guess they had P first in theirs, didn't they? So PA is to PD. So pink blue is to blue red, as pink blue is to blue red, CD. And both, then we'll get another one as well. So we can do the same thing with PB is to, so red pink is to red blue, as red pink, which is now PC in the bigger triangle, is to CD. So now I can rearrange and say, all right, PA is PD squared over CD, and PB is PC squared over CD. Now, what were they talking about? Well, they want to talk about PA over PB. Well, let's do that. PA over PB must be PD squared over CD all over PC squared over CD. And the CDs will cancel out. We'll be left with PD squared over PC squared. take out the square, and that's exactly what they wanted us to show, PD over PC all squared. So no problem. We just had to sort of justify the similar triangles, and then the nice ratios of similar triangles comes in and saves the day. So there we go. Problem number 2 up next. Of course, problem number 3, give it a chance if you haven't already taken a look at it. We'll see. I'll see you for that in the next video.